In this video, we're going to practice with some new data. So let's take a look at it. A researcher is interested in the effects of a psychoactive drug on performance and efficiency and recruits a sample of 36 participants. Each person takes the psychoactive substance every day for 90 days. And after 90 days, each person takes a timed cognitive test that measures performance and efficiency. For the general population, scores are normally distributed with a population mean of 80 and a population standard deviation of 18. So our sample had an average, a mean of 84 on the efficiency test. So we're going to use a two-tailed test with an alpha at 0.05 to determine if the psychoactive substance had any impact on performance. First thing we need to do is determine our hypotheses. We're going to come up with a critical region, and in this case it's going to be 0.05 for a two-tailed test. We're going to collect our data and perform calculations. The mean of our population is going to be 80 and the standard deviation is 18. The n is 36. Our mean is 84. We need to calculate the standard error of the mean, the z-score, and then make a decision. So let's do that. Okay, our first step is to write our hypotheses. I'm going to start with the null hypothesis with a h, a subscript of 0, and I'm going to say the mu is equal to the mean. So the population mean is equal to our sample mean. My alternative hypothesis says, well, actually, no, they are not equal. And I could write it another way too. I could say that my null hypothesis is that the mu is equal to 80, and the alternative hypothesis would be that the mu is not equal to 80. So once we have our hypotheses, we're going to go ahead and look for our critical regions. Let's do that. So for the next step, we have to define our critical region. To do that, I'm going to draw the curve. I'm going to set my critical boundaries here. My alpha level, as we talked about, was 0.05. So basically, I have to take that 0.05 and put half in this tail and half in that tail. So I have 0.025 in this tail and 0.025 in this tail. This is my critical area, my critical region. Now, if I were to look up 0.025 in the tail on the unit normal table, it would give me a z-score of 1.96 here and negative 1.96 here. So now I know my critical region. I know that to find statistical significance, my sample mean has to fall in one of these two areas for me to be able to reject the null hypothesis. So let's do some calculations. Okay, so now we're going to do our calculations. The very first thing that we're going to need to do is find out the standard error. And as a reminder, here's the formula for our standard error. It's the standard deviation divided by the square root of n. So for us, that means we had 18 as our standard deviation, and we had 36 participants. So we have 18 essentially being divided by 6. So our standard error is going to be 3. And now we can apply the z formula now that we have the standard error. Our mean was 84, and the mean of the the mean of the population was 80. And we're going to divide that by 3. So we have 4 divided by 3, which gives us 1.33. So our z-score is 1.33. The last thing we're going to do is make a decision. Okay, coming back to our decision, I have to look at these critical areas that we set up earlier for an alpha level at 0.05. And we have 1.96 here and negative 0.196 here. The z-score that we calculated was 1.33. That's positive, it's above the mean. So I'm going to estimate about where 1.33 as z-score would be. I think it might be about here. Okay, so that we have to make a decision. Is our calculated z-score within the critical area? Is it a high probability event or a low probability event? Well, it is definitely a high probability event, meaning that we're going to take a leap and say there is no difference between our sample mean and the population mean. Any differences that we're seeing are just due to chance, but there is no statistically significant difference. So the decision we made is to fail to reject the null hypothesis. The psychoactive substance did not significantly impact participant performance and cognitive efficiency. That is hypothesis testing. You're getting so good at it, I know. So one last thing on this is we are not going to calculate Cohen's d in this case. Well, why not? We don't typically calculate Cohen's d if there's not a statistically significant result. Okay, in the next video and the last video, we're going to talk about something called power. So one more to go. I'll see you there.